Folks, so we're going to be starting with problem 3 today, and in addition to doing the inverse graph, we are also going to find the inverse equation. So straight away, I'm going to go ahead and write that inverse notation, f to the negative 1 of x, which is read as the inverse of f of x. So my final equation is going to have that as the output label. Now, what type of equation do you think we're going to get when we invert a linear equation? Are we going to get an entirely new function? Based on what we did yesterday, when we started with this original linear function and inverted all the points, we got another linear function. So we should end up with some linear function. So let's go ahead and see what happens when we invert this algebraically. The first thing we want to do, well, the big thing we're going to want to do is switch x and y. But first, we need to get a y in this expression. So we're going to replace f of x with y. So y equals 2x minus 1. Now to find the inverse, we switch x and y. Everything else in the equation stays locked in. So I don't do anything with that 2. I don't do anything with that negative 1. I am only flipping the variables. So x equals 2y minus 1. So at this point, this equation is the inverse, but we want to change it back into a y equals equation. 1, so it looks like slope-intercept form, and 2, so I can replace the new y with that inverse notation label. So folks, if I told you to solve this equation for y, what would we do first? Add that 1 over to the other side, so plus 1, plus 1. So x plus 1 equals 2y. And then we would divide both sides by 2. Now careful, because when we divide by 2 over here, I'm going to have to take the x divided by 2 and the 1 divided by 2. So that will give me y equals, I'm going to go ahead and put the y equals on the left side. So I'm just flipping the whole equation around. Y equals x over 2. And that x over 2 is the same as having 1x over 2. So we can write that as 1/2 x, just because it makes the slope a little bit more obvious instead of just x over 2. So 1/2 x for this part. And then what's our y-intercept going to be? 1/2. So now we are going to take this part and replace the y with that inverse function notation. So the inverse of f of x is 1/2 x plus 1/2. So this tells me, hey, this isn't just any old linear equation. It is specifically the inverse of this original function that we started with. So original function, inverse function. So we switched x and y and then solved for y. Now, yesterday, what we did was we made a table of values for my original function, and then I swapped them, x with y, in order to get my inverse function. Folks, why don't I need to do that with this linear function? Because we can easily graph a linear function. So because for this problem, we have the actual equation, I don't have to find points for this and then invert them. I can just graph the original equation, f of x, and then the inverse equation. So let's go ahead and start by graphing the original function, f of x. So this is a nice review of our last unit. The y-intercept is -1. So bloop, y-intercept down there. And then our slope is 2, so 2 over 1. Rise 2, run 1. Rise 2, run 1. Rise 2, run 1. You don't have to use your rulers. It doesn't have to be exact. But I tell you what you do need to do is label that sucker f of x. So labels are really important here, folks, because we need to denote that this line is the graph of that equation, and that's going to help us figure out which line then the inverse function is. So now, looking at the inverse function, we do have a fractional y-intercept, which I do not love. So there's my y-intercept of 1/2. And then my slope is rise 1, run 2. So I'm going to rise a whole box, which takes me to halfway between these two, and run 2 units. Rise 1, run 2. Now, if you say, whoa, I hate those fractional points, I would much rather do it a different way. Folks, you still have the option of taking these exact points that we got on our original function and inverting them. So for example, this point is 0, -1. What do I get if I invert that? -1, 0. Okay, will do, thanks. Sam, did you already say you're leaving? They just called and said you're leaving at 12. So, all right, folks. So, -1, 0 would be a good point. This point is at 1, 1. So, if I flip-flop that around, we get the same exact point. This point is 2, 3. If I flip it, I get 3, 2. So, with linear functions, you have some options. And where can we write this? Let's actually flip back a page to where we have these graphical instruction options. For lines or linear functions and their inverses, you can use y equals mx plus b for graphing, or you can make tables using inputs and outputs and then invert them. Totally up to you. Slope-intercept form is from the last unit, but if you like finding those exact points and then flipping them, that works too. So you can use y equals mx plus b, or make tables. So let's go ahead and swoosh through those. And we are going to label this our inverse function. So f to the -1 of x, which is read as the inverse of f of x. And the reason why we want to say this is the function and that is the inverse is because when we draw in that line of reflection, we should see how each of those points was reflected. So a reminder from yesterday, that line of reflection is at y equals x, which has a y-intercept of 0 and a slope of 1. It's our parent linear function, the simplest line that we can have. So I'm going to go ahead and go through 0, 0. And then up 1 over 1. You can pretty much go in a diagonal up through the corners of those boxes. And I like to draw in this line of reflection because it is a good way to check ourselves. So does it look like this blue line point moved an equal distance over to the other side? Yep, looks good. This one that hasn't moved, it's exactly on the line. That was that point 1, 1, where if we switch the x and the y value, it's going to be exactly the same. And then this point moves an equal distance across that line. So we draw in that line of reflection because it's a good way to check our graphing and to possibly check our equations. So folks, what questions do we have so far? We're going to go ahead and jump into number 4 next. And what type of function is number 4? It's another line. Oh, hallelujah. So let's go ahead and just graph that line first. It has a y-intercept of 2, so it's going to hit the y-axis at 2. And my slope is 1/3. So rise 1, run 1, 2, 3. Rise 1, run 1, 2, 3. Don't forget to put the arrows on your graph as well. I've noticed on a few of the homework quizzes and things that have been coming my way that some people are leaving those off. We do have to have those arrows because domain-wise, that's what shows that the line goes on and on forever and ever. Also, the label, f of x, that is our original line. So now we are ready to find the inverse. Step number 1 is replacing f of x with a y. Because if I'm going to switch x and y to find the inverse, we have to have a y in the equation. So y equals 1/3 x plus 2. Still the original function at this point. Now, to invert it, we're going to switch just the x and the y. Everything else is locked in. That 1/3 is in the same spot. The plus 2 is in the same spot. But the x and the y switch around. So at this point, it is inverted. But if I told you to graph that, you'd go, it's not in slope-intercept form. It's not in standard form. It looks pretty gross. Plus, we have to have it as a y equals equation so that we can include that important label that says it is the inverse of that original function. So now we are going to resolve for y. So what's our first step? Minus 2. X minus 2 equals 1/3 y. Oh no! We talked about this maybe the, second or third day of school. I've got 1/3 times y. How do I get rid of timesing? We divide, but then I'm dividing by 1/3, which is the same as multiplying by the reciprocal, and then we just start having a brain headache. So instead of trying to do the opposite operation here, we're going to approach this from a destroy the fraction standpoint. We're going to destroy that denominator because what's making this a fraction is the dividing by 3. Well, how do I get rid of a dividing by 3? Times it by 3. So I'm going to multiply this side by 3, and, this is important, this entire left side by 3. Now notice that I have thrown those parentheses in. Just like on this one where I had to divide both the x and the 1 by 2, over here I'm going to have to multiply both the x and the negative 2 by 3. So let's go ahead and distribute. So 3 times x is 3x, and 3 times negative 2 is negative 6. And then this is equal to, I wish I had more room over here. That multiplying by 3 cancels out the dividing by 3, and what are we left with? 1y or just a y? Our final step is to replace that y with the inverse function notation. So f to the negative 1 of x is read as the inverse of f of x is equal to 3x minus 6. Now 3x minus 6, that's a nice friendly slope-intercept form equation. It doesn't scare me too much. So I don't think we need to make a table for this one either. Let's go ahead and graph that y-intercept at negative 6. 1, 2, 3, 4, 5, 6. And then our slope is 3, so rise 3, run 1. 1, 2, 3, 1. 1, 2, 3, 1. Ooh. Anytime I hit the original function, I get kind of excited because that tells me that that point is going to have the same x and y value. This point that I just hit is 3, 3. So what happens when I flip 3, 3? It's still 3, 3. So that point with the same x and y value is on both lines. And swoosh. And we're going to label that one the inverse as well. So label on the equation, label on the graph. And our final step is going to be drawing in that line of reflection, which is just kind of a nice check that everything looks good as far as reflecting over that line. Through 0. And with a slope of 1. Does it look like all of our points have moved in equal distance across that line? Yep. One little side note that I want to add about this, just because this is something that you're going to see later if you go on to take pre-calc, but Remember how with graphing lines, it's kind of like, oh, we graph them, neat lines. But then we get to linear programming, and it's like, oh, there's actually kind of a cool application with this. It's the same thing with inverses. It's like, all right, we're switching the x and y around, and then we get this other equation where the input and output are switched. So just for fun, I'm going to show you one of the real-world examples for what inverses are used for. On your phone, you have a contact list. And that contact list, you look up someone's name, and what does it dial out? Their phone number. And then, on the other person's end, they have caller ID. If they have you in their contact list, and what goes into their phone is the phone number, but what shows up? Your name. So this is a case where our X and Y's switch. My name is the original input. The phone number is the original output. On the other end of things, that Y value is coming in and it outputs as a name. So X and Y are switching for these two inverse functions. You see inverse functions a lot with like Google, reverse lookup, things like that. So inverses come up a lot in certain types of programming, searching databases, things like that. So yes, X and Y are switching and we're having so much fun making these graphs, but this actually has a lot of implications for programming. So hopefully that gives you a little bit more buy-in on why we're doing these. Let's go ahead and, we're going to do this quadratic one down at the bottom first. Now, we had a quadratic one up here, but then its inverse looks like this. Now, hold up a second. We've been doing a whole bunch of transformations, right? What can I do with those normal transformations that's going to flip me over this line instead of the y-axis? So in all of the quadratics we've seen, they've all been, my parent function and then maybe a narrower one, maybe an upside down wide one. But we have never had a sideways one. So I want to kind of give you a preview with this because when we find the inverse equation, it is going to be a different function. So take a deep breath. And we're going to start by just graphing the original function. So we are going to have to show a bit more work on this one because this involves using our transformation rules. So what is the parent function of this? It's a quadratic, or y equals x squared. What does that parent table look like? -1, 0, and 1, 1, 0, 1. And I'm not even going to graph the parent function because I don't care about parent functions on this problem. We want this function and its inverse. So folks, what's that +2 on the outside doing to my parent function?
Moving it up 2.
Up 2. And up 2 is going to be affecting my y values. So y +2. So my actual function, f of x, is going to have this for a table. We'll have -1, 0, and 1. Those x values stay the same. And then the y's, we're going to add 2 to all of them. So 3 and 2 and 3. So this is the parent. And we use that to graph the original function. So let's plot those points. Backwards 1, up 1, 2, 3. 0, 2. 1, 3. Swoosh. And let's label that f of x because that is my original function. So does everyone see what we did there? In order to graph this function, I had to use transformation rules on the parent function to get some points that I could plot. Way different than slope-intercept form because I can't just pull out the key features just from looking at the equation, but we can pull out the transformation rules. So folks, I want you to flip back a page. So bright. And underneath where we wrote linear, I want you to write quadratic. Use transformations and make tables. So for a quadratic, use transformations and make a table. All right, so flipping back, let's go ahead and find the inverse graph before we find the inverse equation. So because I had to already make a table that has nice easy points with it, we're going to go ahead and use this to get our inverse table. So how do we find those inverted points? We flip-flop all those x and y values. So instead of -1, 3, we'll have 3, -1. Instead of 0, 2, we'll have 2, 0. And instead of 1, 3, we'll have 3, 1. So we inverted the f of x table to get the inverse table. So now plotting these points, forward 3, down 1, 2, 0, 3, 1. Put your arrows on and label it the inverse of f of x. And let's go ahead and draw in that line of reflection as a check. It goes through 0, 0, and it has a slope of 1. Does it look like every point has moved an equal distance across that line of reflection? Yep, it all looks good. Folks, any questions on the table side of things before we move to the equation? I can do this. I can do this. Let's go ahead and start by replacing f of x with y. And let's go ahead and kind of start up here a little bit. So y equals x squared plus 2. Just replacing f of x with y so that for finding the inverse, we can just switch the x and the y around and not have to worry about all that old f of x. So we switch x and y, and we get x equals y squared plus 2. So notice that the squared stays locked in, just like we've done previously with those coefficients. So if I asked you to isolate y, what would we do first? Minus the 2. Perfect. So minus 2. Minus 2. So then, don't mind me. I'm going to switch the order around. Put the y squared over here. And the x minus 2 over here. So we need to try to get the y all by itself. But right now, y is squared. So if we think about solving and using opposite operations, what's the opposite of squaring something? Square root. Square root, square root. And here's our first new piece of info. Anytime you square root, you have to include a plus or a minus in front of the square root. So then our inverse equation, replacing that y with f to the negative 1 of x, would be plus or minus the square root of x minus 2. Now, if I were you, I'd be looking at that going, I don't like that. And I'm not really sure why we need that plus or minus there. So I'm going to give you a concrete example
for y, square root requires that I put a plus or minus there. We're going to start with this equation. X squared equals 9. If I want to solve for what x is, square root. And x is equal to 3. But what else squared could give me 9? A negative 3. So because there are two solutions to this, because positive 3 squared gives me 9 and negative 3 squared gives me 9, I always have to include a plus or minus. So when you hear me say square root, I want you to also think of that plus or minus symbol that goes with it. Because squaring a positive gives me a positive and squaring a negative gives me a positive. There's always going to be two cases for it. Folks, questions on that plus or minus? Because now we're going to see what it means for our graph. So if I look at this inverse equation, it's a square root function. And it's like, well, we've been seeing square roots before with our parent functions, but what does the plus or minus do for it? That plus or minus actually makes this two separate equations. The first equation is positive square root of x minus 2, and the second equation is negative square root of x minus 2. So let's see what that means for this graph. First, a square root function with a minus 2 on the inside. What's that minus 2 doing? Right 2. So right 2. Does it look like this inverse has a vertex that's been moved to the right 2? Yep. So that part looks good. But then what about the sign difference between these two? This one is just a positive square root function. So a square root that curves up from the vertex. What is this one doing? What's that negative out in front of the square root doing? It's vertically reflecting it over the x-axis so that this part of the equation is curving down. So that is how we get a sideways parabola. It's made up of two square root pieces. One of them is curving up, one of them is curving down, and that is how I algebraically can get that shape. Mind blown, right? It's pretty crazy. Folks, we're going to go ahead and take a bathroom break, phone break before we move on to the next section.